So our first speaker is Anand Kashyap, co-founder and CTO at Fortanix. In today's session, Anand will discuss the state of affairs with the PQC algorithms, their state of development, as well as adoption and usage in the industry. A bit about him: he is the co-founder and chief technology officer at Fortanix. He previously worked at Symantec and VMware as a researcher and an engineer in the areas of security and networking. He has presented at financial cryptography and Black Hat conferences and has filed over 25 patents. He holds a PhD from Stony Brook University and a Bachelor of Technology from IIT Kanpur, both in computer science. Please welcome Anand Kashyap to the stage.
Hello, everyone. My name is Anand Kashyap. I'm co-founder and CTO of Fortanix. Fortanix is a cybersecurity company. We do data security in multi-cloud. And today's topic is, are you ready for PQC? So let's learn more about what PQC means, why you should be caring about PQC, and if you're ready for PQC. So for the last 40, 50 years, there have been a huge increase in computing, and the modern computing is all based on some of these things that you might recognize: bits, zeros and ones, transistors, gates, microprocessors, and there have been huge advances in the technology in the development of microprocessors in the last 40, 50 years. And that has led to the computing revolution we all know about. Now, coming to the modern world, this is a question that keeps coming up these days. While the modern computing is all based on measuring voltages and currents, and all the semiconductors and the gates and transistors are built on top of that, what if instead of measuring voltages and currents, you could measure the quantum properties of subatomic particles and use that as the basis of doing modern computing? What if computation can be performed in particles at quantum levels? And how does that change the way computing is done? So if you think about that, instead of thinking of your regular diode equation where you pass the current and then you get a 0 or a 1, you start thinking of a Schrodinger equation, where instead of a 0 and a 1, you get some uncertainty, you get multiple states a bit can be in. So it could be 0 or it could be 1, but with a certain probability. And that concept of having a probabilistic state at the quantum level forms the basis for the modern quantum computing. So the way it works is, instead of bits that you use in your classical computers, you have qubits. And what's a qubit? A qubit represents a quantum state, which is either a 0 or a 1 with some probability. And how do you create these qubits? So there have been many implementations using different material, different particles. An example of that is a subparticle with quantum property like a spin as state. So you need some particle that denotes a state, and then there's an extra probability which comes from, for example, a subatomic particle can have different spins at different times. So that gives the state. And this is one implementation which can be used to create qubits, and then qubits form the basis for quantum computers. There have been a lot of research going on in recent times on quantum computing. You might have seen pictures like these. Google recently built a 54-bit quantum computer. IBM has been working on quantum computers as well. So there's a race going on who can build the faster, the better, the more stable quantum computers. Google also claimed quantum supremacy recently in 2019. And what does quantum supremacy mean? It means that using a quantum computer, they were able to solve a problem or create an algorithm for a problem which would have taken about 10,000 years for a supercomputer, and they were able to do that in about 200 seconds. And they claim this is when they achieved quantum supremacy for that specific problem and for that specific algorithm. So why is all this important? Yes, quantum computers are here. They're much faster for some algorithms compared to classical algorithms. But what does it do to cryptography? And this is very important, and that's the matter that we want to discuss today in this presentation. So what researchers have done is, in the recent times, using quantum computers, they've come up with a few algorithms which quantum computers are particularly good at solving when compared to classical computers. One example of that is Grover's algorithm. What Grover's algorithm does is it allows for brute force search to be done in square root of classical time. So for example, if you're doing a brute force search for something in a list of size n, so instead of taking time of the order of n, it would only take you the order of square root of n to perform the search. So what's the implication of Grover's algorithm? The implication is that it can weaken many algorithms, where the only way to break the algorithm will be to do a brute force search. Now that brute force search becomes much easier. So if you are using AES 128-bit, square root of 2 to the power 128 is 2 to the power 64. So an AES 128-bit implementation now only has security equivalent to a 64-bit implementation. And 64-bit implementation takes 2 to the power 64 times. So it's much easier to do the brute force search when compared to something which is of the order of 2 to the power 128. So Grover's algorithm, which allows quantum computers to do search much faster, brute force search much faster, weakens a lot of algorithms. The other algorithm, which was proposed by Shor in 1990s, it's called the Shor's algorithm. And that has even more profound implication. So what Shor's algorithm says is that using quantum computers, there's certain algorithms which can be done very efficiently in polynomial time. Things like number factorization, things like discrete logarithm problems. So solving these problems becomes much, much easier using quantum computers. And what's the implication of that? If you think about how RSA is implemented or elliptic curve is implemented, RSA is implemented, assuming that factorizing large prime numbers, the product of prime numbers is very, very hard. But with quantum computers using Shor's algorithm, now that becomes easy. So the implication is that RSA is broken. Similarly, ECC, or elliptic curve cryptography, is based on the assumption that solving these discrete log problems is very, very hard. But again, with quantum computers and Shor's algorithm, this becomes easy. What that also means is that elliptic curve cryptography is broken. So the implication is huge with quantum computers. All the modern public key cryptography, which is based either on RSA or based on elliptic curve cryptography, they're all broken. And that is used everywhere. It's used on the internet. It's used for code signing. It's used in TLS. It's used in all the places that we know. So this is huge. So all modern asymmetric private key cryptography that is being used in today's world will be broken when quantum computers become real. And the symmetric key cryptography become easier to crack. So what do we do? This is all may sound like doomsday. Once quantum computers come, all cryptography is broken, really, really bad. But researchers and scientists, they recognize that. And they have been working on a new way to do cryptography in the last 10, 20 years. And this new area of cryptography is called post-quantum cryptography. So what is post-quantum cryptography, or PQC, as it is widely known? This is a set of cryptographic algorithms that can run on today's classical computers, but are resistant to quantum computers. The idea is that can you build crypto algorithms which will not be broken even when quantum computers become real. And the idea is you should be able to run these algorithms on classical computers. So these are different from quantum cryptography, which is a type of cryptography supposed to run on quantum computers. Post-quantum cryptography actually runs on classical computers, but is resistant to quantum computers. So if you're building post-quantum cryptography algorithms, now you need to think, how do you build these algorithms? Because Grover's algorithm told us that small linear-sized lists can easily be explored. Brute force search is easy if the list size of the list is not very large. Shor's algorithm said that you can't build an algorithm which relies on factoring an integer. We can't build an algorithm that relies on computing discrete logs. So what can work? So what can work is you still use or rely on Grover's algorithm, which says that small lists can be easy to brute force, but large lists are still okay. What that means is that if you can build algorithms which are harder to do brute force, then they can still work. So researchers have been working on creating algorithms which require solving hard mathematical problems that even a quantum computer can't solve in a reasonable time. So algorithms which are based on hashing, algorithms which are based on some symmetric cryptography-like techniques, which require large key spaces, may still work. There have been multiple approaches to creating post-quantum crypto algorithms. People have used techniques such as building code-based crypto systems, which relies on error-correcting codes. And this is a technique where you can do encryption faster, but then the key sizes become very large. Similarly, there have been a category of post-quantum crypto algorithm implementations which rely on lattices using techniques such as learning with errors or LWE and TRU. These are also very fast, but they have very large key sizes. Another category of post-quantum crypto algorithms, and these were one of the early ones to be developed and standardized, and they are based on hashes, on computing hashes. Because again, if you go back to the Grover's algorithm, which makes brute force easy, but if you're dealing with large spaces to explore, then it's still difficult. So that's what this set of algorithms relies on. And this is easy to analyze, but what people have found is that this is difficult to scale. The earlier implementations of hash-based crypto systems were stateful, which means that every time you use a key and you sign something, the next time you want to sign something, the key changes. So you need to maintain that state. And that becomes quite cumbersome. So the algorithm itself is easy to understand, but the implementation and making sure that the state remains consistent, that becomes a challenge in the implementation. However, there have been new algorithms which are stateless that have been implemented for hash-based crypto systems. We'll touch upon some of the algorithms that have been standardized in a bit, which make that problem easier. But again, there's still problems around speed and the size of the keys. So since post-quantum crypto became a major area of research for cryptographers in the last 10, 15 years, and people realize that quantum computers are coming, and the current algorithms will all be broken. There's been a huge amount of work in finding new algorithms, standardizing them, and standardization bodies like NIST actually ran a competition where they invited submissions for post-quantum crypto. They got more than 65 or 70 algorithms as submissions. And then they went through multiple rounds of scrutiny testing before a few algorithms were finalized. So among NIST and the European body of standardization, there have been a few algorithms which have been standardized. Some have been approved by NIST. Some are in the final process of being standardized. Most recently, in 2022, this year, a few months ago, NIST announced its final set of algorithms that were standardized as well. And here's a list of all the algorithms that are currently standardized and can be used for PQC. The first two, LMS and XMSS, they were the early ones to be standardized. Both of them are based on hash-based cryptography, and both of them are stateful, which again have that property where when you do the signature, the next time the key changes. The public key does not change, but the private key keeps changing. And both of these are used for doing digital signatures. Among the newer algorithms that have been standardized, there are some which allow you to do encryption and key exchange, and the other ones allow you to do signatures. So Crystal's Kyber, Crystal's Dilithium, they're both based on learning with errors based cryptography. And Kyber allows you to do encryption and key exchange. Dilithium allows you to do signatures. Falcon is based on NTRU and it is used for signatures. Macaleese is based on code-based crypto systems, and that is used for encryption and key exchange. Sphinx is similar to LMS and XMSS, which means it's based on hashes, computing hashes, but instead of being stateful, it is stateless. It's also used for signatures. So while there are so many algorithms, it's important when we are implementing PQC to consider what the use cases, because some of the algorithms, they may have different usages, while some are used for computing signatures, some are used for key exchange. Some of them may have large keys compared to others. Some of them may be slower or faster than others. So depending on the use case, different algorithms will be used in different situations. And if you're implementing PQC, it's important to understand what the differences are, what is your specific use case, whether you care about speed, whether you care about space, what application you're building, and then you choose the right PQC algorithm based on that. So all that is good. We saw that quantum computers are coming. They break classical cryptography. The good news is now we have PQC and there are new algorithms which are being standardized. But why should you care? And why should you care about it today? So this is important because if you have a high-value key which you're using for doing digital signatures, for doing public key cryptography, quantum computers are not 50 years in the making. There's some implementations of quantum computers that already exist today. And if there's a motivated adversary, they can build a quantum computer and they can try to break your high-value key even today. And the research on quantum computers is going on. And very soon we will have quantum computers which are easy to produce, which are not as expensive as they are today. And this will continue to become easier and easier. The other scenario where you should care about PQC is, let's say you have a key material that needs to be protected for a long time. So maybe you think quantum computers are not available today, but maybe they'll come in 5 years, 10 years. But you may have some places where you have keys which are not going to be rotated in the next 5 years to 10 years. When was the last time you rotated the root key for your PKI system? Probably a long time ago. Some of these keys continue to be in use for a very long time. And if quantum computers become practical, then those keys will be broken. Similarly, there are web certificates, code signing keys. A lot of them don't get rotated very often. The other scenario where a key material lives in products such as IoT devices, industrial IoT, you might have several of those devices even sitting in your own home. if you have a smart TV, a smart thermostat that's sitting on your wall, now that thermostat is supposed to work for 10, 20 years. Similarly, if you have a personal healthcare device, a lot of those devices have keys these days. Something might be embedded in your body, and they're not supposed to go out of use in the next 10, 20 years. Guess what? In the next 10, 20 years, quantum computers will become real. And then the key material that lives in those products will be vulnerable. So you should care about PQC today and not think that, oh, this is still 10, 20 years out and let me worry about it when this becomes real. So wherever you have keys that are supposed to live for a long time, maybe your keys live in some product which is already out there in the field and you can't go and replace the keys in there, then you should be using PQC today. Who is using PQC? So there is a lot of places where people are already starting to use PQC. Cloudflare wrote a blog this month, actually, where they said, oh, we are post-quantum ready. They offer post-quantum in the implementation globally. So what they have implemented is a kind of a hybrid key agreement during TLS handshakes. So they're not doing signatures during the handshake, but they're doing the key agreement part, and they support it using the Kyber algorithm for which has been standardized for PQC. However, that does require you to go to that website supported by Cloudflare using a supported browser or an app that also supports PQC on the client side. Similarly, Google has been doing a lot of research on PQC, and they've been preparing for a post-quantum world as well. And they've written a blog on what are the steps they are taking to get ready for PQC. And they've also implemented a hybrid key agreement similar to Cloudflare. OpenPGP has been working on drafting the inclusion of PQC algorithms into the PGP suite of algorithms. So there's been a lot of work going on over there. Similarly, OpenSSH has been experimenting PQC as well. So these are some of the examples where people have talked about openly standardization efforts as well as implementation in production systems. But we'll see more and more of this going forward. So what's our recommendation? How do you use PQC? Now that hopefully I've convinced you that you should start thinking about PQC, you should start implementing PQC today. How do you use it? So one thing is you should think about crypto agility. So as we saw, there are about 6 or 7 algorithms that have been standardized. However, this is still a very new field of cryptography. It's not like RSA or elliptic curve cryptography, which were standardized and used over a period of 20, 30, 40 years. This is something new, which means that new algorithms may come. Maybe some of these algorithms may get broken, who knows? So when that happens, you should practice crypto agility, which means you should build applications where you can switch or change algorithms as they come. You should be following NIST recommendations. You should be looking at research findings in this area. You should be implementing PQC in a way that you're implementing cryptography these days anyway, which is make it API friendly, make it DevOps friendly. There are implementations where you can just plug in a REST API and you can start doing digital signatures, for example. So you should be using that. You should be doing centralized monitoring management as you'd do for a key management and cryptography and encryption system. So how can Fortanix help? Fortanix has a product called Data Security Manager. Data Security Manager is an HSM. It's a FIPS 140-2 level 3 certified HSM. It's also a key management system. And if you use Fortanix DSM, we are already post-quantum cryptography ready. So it is in production. It is enterprise grade. We already support PQC. The algorithm that we implemented first is the LMS algorithm, which is based on hash-based cryptography. It uses a stateful hash-based algorithm, and the way Fortanix DSM is deployed is deployed as a cluster. The cluster maintains strong consistency of data, and that is really important for an algorithm like LMS, which relies on maintaining state, and the state should be consistent across multiple nodes in a cluster, because you want high availability for your keys. You want disaster recovery for your keys as well. So while getting HADR, maintaining consistency of state, all of that is already built into DSM, Fortanix DSM. So you can start using it without having to worry about how do I maintain state, how do I maintain consistency of the state. Fortanix DSM is offered as SaaS. It gives you strong authentication, authorization, quorum-based controls for all types of keys, including PQC. The way you use PQC is, again, you create a key and then you make an API call to perform your digital signatures in case of LMS, for example. And all of these are available using REST APIs. So while we have seen people use our LMS implementation, we're not just going to implement that one specific algorithm. We are also looking at all the other algorithms that have been standardized by NIST, and over time we'll be implementing and supporting all the other algorithms. Right. With that, I'd like to thank everyone, and happy to take any questions. Thank you.
Hi, Anand. Thank you for joining us. How are you?
I'm good. Thank you.
Thank you. We have quite a few questions here for you, so I'll get started. In classical encryption like AES and RSA, a random number bit generator is an important building. Do you suggest using quantum random bit generators? And is there a standard?
I think the random number generation itself is quantum safe, so we don't need to worry about using a quantum computer-based random number generator. With PQC, what we're trying to do is being able to run algorithms on classical computers, which will still be safe when quantum computers become real. And the two algorithms that we worry about the most are the Shor's algorithm, which break things like public key cryptography, RSA, ECDSA, and others, and the Grover's algorithm, which provides a brute force way to search in a list, and that weakens a lot of cryptography where the key strength is not very large. But the random number generation itself is not broken by any of these algorithms. So from today's research, I think it's safe to continue using NIST-approved random number generation.
Okay, thank you. The next question here, what is the threat quantum computing poses to current cryptography?
Yeah, so as we saw in the presentation, modern cryptography, there are two types of cryptography. There's symmetric cryptography, symmetric encryption, and then there is asymmetric cryptography, which forms the basis for PKI, for digital signatures. For symmetric cryptography, generally there are algorithms like AES, where you use a random number-based generated key, and then use it for encrypting data. And the impact of quantum computers is that the key strength needs to be much stronger for symmetric cryptography. So AES 128 will no longer be secure, but AES 256 should be okay, even with quantum computers. On the other hand, public key cryptography, whatever algorithms are being used today, they will all be broken. So RSA, elliptic cryptography, all of those rely on solving a hard mathematical problems. And that hard mathematical problem becomes easy to solve with quantum computers. So those algorithms no longer are safe. So that's why there's a new set of algorithms being developed, which will be post-quantum cryptos, which are in the category of PQC and which are safe even when quantum computers become real.
Okay, thank you so much. I've got another one that's come in here. As indicated, PQC is designed as the next step for classic crypto. For identity, authentication, and signatures, we rely keys being embedded in standard compliant times 509 certificates. The question is, are we looking to define a certificate format that can carry 2 or more keys to allow transition experiences to be less binary?
Yeah, so there's work going on in building certificates which rely on quantum safe or PQC based algorithms. We've not seen them rolled out in practice yet. And the implementations we have seen for PQC in the field, the one from Google or Cloudflare, they're still not using PQC based certificates. They're using PQC for doing key agreement, hybrid key agreement during the TLS handshake. But we have not seen certificates being rolled out which can do digital signatures with PQC algorithms. Hopefully that will change and some of those things will become real.
Okay, thank you. What is involved in replacing quantum vulnerable cryptography?
So there are many places where we're using quantum algorithms which are not safe from quantum computers. There is a TLS, which is used everywhere. It is used on the web. When you connect to your bank's website, you're using TLS. There is code signing, which is used to sign software that we use. There is the firmware signatures, which are used to sign the firmware for IoT devices. So as you're looking to migrate from classical crypto to post-quantum crypto, you should look at each of these use cases and evaluate which one is the most critical to go and replace or upgrade and go from classical to post-quantum crypto. So quantum computers are becoming real, but they're still not widely available. They're still not easy to buy or start using. So if you have a certificate which is only valid for 6 months or 1 year, maybe you don't need to worry about quantum cryptography for those kind of use cases. So most of the TLS certificates, maybe they're not very long-lived certificates, so that you're okay. But places where you're doing firmware signing for IoT devices, which are going out in the field, which are supposed to work for the next 10 years, 20 years, that is one area where you should be worried. And you should be thinking of, okay, and the next time I sign the firmware for this IoT device, I should be using PQC. Similarly, there could be software which goes outside of your boundary of control and goes in some other environment and runs there. And it's expected to run for 5 years, 10 years, or maybe it's in the hand of the adversary where they do have access to high-powered quantum computers. And there you'd want to use PQC today.
Okay, and that kind of leads into this question. Quantum being a new tech can be expensive, which it shouldn't and isn't accessible easily to everyone. What's your thoughts on that?
It is expensive today, just like any new technology. When it starts, they're expensive, they're hard to get. If you go back 20, 30 years, even internet was not widely available. People had modem devices and they'd connect very low bandwidth internet connections. But look how things have changed in the last 20 years. So who knows whether this technology will become easily accessible, whether it will become cheap. Today it's not, but there is a lot of research going on today. Companies like IBM and Google are spending a lot of money doing research, building particles, doing research all the way from particle physics to material science to computers and software. So these things are being developed, and people see usage in military use cases as well as other use cases. So I think people have been predicting for the last 10 years that quantum computers will become available and real in the next 10, 20 years. Some people still say that 10 years out, but maybe in the next 10 years, we'll start seeing them more widely available.
Yeah. Okay. Thank you, Anand. That's all the questions that I have here. I really appreciate you being live and for your presentation. Thank you for your time today.
Thank you very much. Thank you for having me.
Thank you. Our next speaker